Hello friends, a very good evening to all of you, and now we'll look into some more concepts of electrochemistry. Okay, so first of all, let us start off with some concepts from physics. Right, okay, so what is resistance? Resistance is given by, you can say, R is equals to rho L by A, where your rho is your resistivity, L is this whole thing is actually your called cell constant. L by A is called cell constant. L is the distance between two electrons. Okay, and A is the area of cross section of the electrodes. Right, great. So this is resistance resistivity, and so L by cell constant, the unit is centimeter by centimeter square, which give you centimeter inverse. And the reciprocal of resistance is your conductivity. And resistance, the reciprocal is conductance, which can you can see given by G is equals to 1 by R equals to 1 by rho A by L, and 1 by rho you can write it as kappa, which is conductivity. Okay, this is conductivity. So the unit of resistance can be, as you know, ohm, right? And the unit of conductance is, you can say it in mho or ohm inverse. And okay, so and you can easily find out the unit of resistivity, like this. If this is ohm, so this will be ohm into centimeter square by centimeter, or whatever the unit may be of centimeter or meter. Similarly for conductance as well. And now we'll talk about your equivalent conductance. That is your supposed conductance given by lambda, capital lambda or G. So equivalent conductance EQ is equals to kappa into 1000 by C equivalent. So kappa is our conductivity, 1000 is just like the factor which comes when we use the formula, and CEQ is our concentration of the electrolyte in equivalence per liter. So it's concentration in equivalence per liter. Okay, great. And similarly, we can also say that our molar conductance lambda m is equals to kappa into 1000 by Cm, right? Where Cm is concentration in moles per liter. And the relation between molar conductance and equivalent conductance is that molar conductance is equal to your molar mass by equivalent mass into, this is molar conductance, okay, and this will be into your equivalent conductance. Okay, so let's just see the equation one more time, that molar conductance is equals to molar mass by equivalent mass into your equivalent conductance. Okay, and why does this, like it is molar mass by equivalence? If you just match the units on both sides, the factor remaining will be molar mass by equivalent mass, right? So actually, if you see, sometimes all these things are very tricky to remember, whether it's which one is above, which one is below. So you can just remember, if you do something like lambda m by lambda eq, you will get molar mass by equivalent mass. So it's, you can say, it's very much directly proportional to the mass. For just remembering sake, you can use this trick. It's directly proportional to the mass. Okay, and having the physics covered up, I'll move on to the concept of infinite dilution. Infinite dilution. which says it's only for weak electrolytes. Okay, first of all, it's for weak electrolytes, that says the degree of dissociation, which is going to be alpha. It is the degree of dissociation, alpha is equals to your molar conductance at a particular concentration, but you have a molar conductance at an infinite concentration. Okay, so your the degree of association at infinite dilution. So we have the molar conductance at a particular concentration divided by the molar conductance at our infinite concentration, right? So it's only for weak electrolytes. Now we come to the famous Colrusch's law or Colrusch's law. I exactly don't know how it's pronounced, but something like Colrusch's law. So what it says is that at infinite dilution, when at infinite dilution, what will happen? When you dilute everything, it will be total dissociation, right? So when dissociation is complete, when dissociation is complete. Okay, my pen, the nib of this pen is, I hope it works for another 4 months. When dissociation is complete, the each ion, okay, this is the condition, okay. What does Colrusch's law say? That at infinite dilution, when dissociation complete, what will happen? So what will happen is that each ion in the solution will make a contribution towards the conductivity. Contribute to conductivity. So let us put this in mathematical terms right now. So suppose, okay, I think the best way to understand this is actually via an example, but I'll just give you a mathematical form as well. So suppose our total molar conductivity is given by capital lambda to the power. So this is our total molar conductivity, and our individual molar conductivities of the anion at infinite dilution. So this infinity means an infinite dilution. For cation is this, and for anion is this. Okay, and there are, you can say, there are V plus number of this cations, there are V minus number of anions. So our law says that this total molar conductivity will be equals to V plus lambda infinity plus V minus lambda infinity minus. So what does it say? That every cation is contributing to this, right? Because there were V plus cations, there were V minus anions. So every anion is contributing to our molar conductivity. So let us now take an example of Colrusch's law to understand it, and after that we'll take some example of resistance, conductivity, and all those things. Okay, so first let us look into this aspect of Colrusch's law. Great question. So let me use a different color for giving question. I think blue or green. I think I should use blue color. Great. So calculate the molar conductance of NH4OH. Molar conductance, calculate this at infinite dilution. What will be this? So this is our question. What are the given conditions, or our what do you say? Our given facts is that the that molar conductance at infinite dilution, okay, for your beryllium hydroxide, BaCl2, and NH4Cl. So these are given. So for beryllium hydroxide, the molar conductance in infinite dilution is your 523.28. For for BaCl2 it's 280, and for the last one it is 129.8. and they have given a unit for this: ohm inverse centimeter squared per mole inverse. Great. And now we have to find out the molar conductance and dilation for NH4OH. Let me write the answer in green. Answer. Okay, so now what we will do is that we will apply, we need to know it for NH4OH, and now we are given this. Okay, so we need this NH4 and we need this OH. Okay, and our Coriolis law says that every anion will make a contribution. So it says that, as an insect in my table. Okay, so it says that for beryllium hydroxide, every anion and cation will make a contribution. That means that, just one second, let me just get this insect out. Great. So I have successfully killed the insect. And now I'll do the problem. So for beryllium hydroxide, it means that both beryllium and the hydroxide anion will contribute. For BaCl2, it means both beryllium and the chlorine will contribute. For NH4Cl, it means that NH4 plus ion and the Cl minus ion will contribute. But what we need NH4OH, right? So we need to like have this on the right hand side because we need this as a product, right? And that means we need to cancel out Cl minus, we need to cancel out Ba2 plus, and the way to do is if we have to reverse this equation. This equation 2 we need to reverse, right? So let us reverse it. And also you see, to cancel it out, we actually because there are two Cl minus and there's only one Cl minus over here, right? So there's 2H minus, and so we need to also multiply and divide by 2 something. Okay, because if we don't do it, then the 2 Cl minus will not be cut. So what we can do is we can multiply the last equation by 2 into 2. So we reverse the second equation, we multiply the third equation by 2, and what the result is we get is that our beryllium hydroxide stays as it is, right? 2H minus, and let me just take some more space. Beryllium chloride will be reversed, so this will 2Cl minus plus Ba2 plus, giving you BaCl2. So I'm just writing equal sign. You can just for like because I'm writing quickly, I'm writing equal signs. You can write the arrows as well if you want. And this is multiplied via 2. So this will be 2NH4 plus. Sorry, so 2NH4Cl, giving you 2NH4 plus and 2Cl minus. So now let us add all these equations. Okay, so let's see what happens. We have 2. So what we get. Let us cancel out what we can cancel out the Cl minus, we can cancel out the Cl minus, we can cancel out Ba2 plus Ba2 plus. Okay, great. So ultimately, if we just look at the ions, right, what are the ions that are left? The ions that are left are NH4 plus and OH minus. That is what we need because we want it for we want it for you can say for C. So I'm not going into the depth of the molecules. We just need the ions. Okay, so we get these two ions left, but these are in 2, so we need to divide this by 2. Divide by 2. So the main thing is that when we multiply by 2, when we multiply the 2, the molar conductance will be multiplied via 2. When we reverse it, the molar conductance sign will be reversed. Okay, so that is an important thing that you should know. So let us see. So molar conductance for we reverse BaCl2, right? So when we reverse, so the molar conductance will become minus 280. We multiply this one via 2, so this will actually become 129.8. So that's like 130. So it will become around 260. Okay, so our final will be, I'm just writing it over here, and we added all the three, and in the end we saw that we need to divide by 2 as well. So it will be 523 minus 280 plus 260, and what we get is something around your 240. What do we get actually? Hmm, this is like a minus 20, and so just one second, let me just see it. Yeah, so it's right only. Okay, did I make any mistake? It shouldn't be. Okay, so what they have done is adding 3 and 4. Okay, okay. No, I don't think I made. So okay, let me just do it and let me then check the answer. Okay, otherwise, really problem. So what is this? Minus 280 plus 260 is minus 20, and this 523 minus 20. So that is somewhere equals to your, so 523 minus 20 is 503, right? So 503 comes. So, and in the end, as you saw, that we actually, where did my mouse go? Hmm. So in the end, as you saw, that we actually have to divide by 2 because we have 2 in the front of the stoichiometry. So this will be actually 503 by 2. That will be somewhere equals to 250, right? So our answer should be around 250, and the answer that is given is 251.44. So we actually did some approximations, as I saw, with the decimal places. So actually we got the right answer, right? So you understood how easy it is. You just need to see and cancel the ones in the right fashion so that you get the final target equation. If you know, have done Hess's law in thermodynamics, it's a similar fashion. You see, first of all, what is the target thing? You need NH4OH, right? So you need NH4 plus and OH minus. Okay, and for that you need to actually subtract and add some things so that you get finally NH4 plus and OH. So we just manipulated, reverse this, multiply this by 2, finally divide by 2 to get our answer. So that is how it's done. And now let us look into a problem of our resistance and conductivity. Right. Again, let me use the blue pen for question. So question is this, that for 0.01 molar NaCl solution which has a specific conductance. Specific conductance means conductivity. It means your kappa. So kappa is equals to 0.002768 ohm inverse centimeter inverse. The resistance that was given R is equals to 82.4 ohm. Okay, so this was a like given conditions, and now like uh, this is filled with, okay, this is a cell, and this is now filled with your filled with 0.05 normal K2SO4, which has resistance of R is equals to 324 ohm. Okay, so this was a cell, and now this is filled with this. So first question is this: find cell constant. Okay, let us do this first. Okay, so we have the equation, like we have the knowledge. We have kappa, we have R. Okay, so let us try to do this. So R we know is rho L by A, where rho is resistivity, and our kappa is 1 by rho, right? Conductivity is 1 by resistivity. So if kappa is this, rho will be 1 by 0.002768. Cell constant it was. Cell constant is L by A. So we need to find this out. We know R. R is what? 82.4. So our answer L by A will be equal to your uh, 0.02 0.281 centimeter inverse. Right. So we got the first answer. So see, question looks tough, but as I have told you in the morning as well, that the people who progress courageously get something in exam and in life. Okay, so it says now find the specific conductance of 0.005 normal K2SO4. Okay, specific conductance of 0.05 normal K2SO4. So great. So over here we have the concentration, we have the R, we have to find specific conductance. Okay, but we don't need the concentration as of now, because specific conductance actually means your as what I was saying, it actually means your like see, the equation was this, and we have to find the specific conductance. So if we find rho, that is a resistivity, and we reverse that, then only we can get specific conductance, right? Because specific conductance is nothing but conductivity. So we know R is 324 is equals to rho. We know cell constant, we just got it. Cell constant remains constant for every equation. So we get rho like equal to something, and our specific conductance kappa will be 1 by rho, and that will be equal to 7 into 10 to the power minus 4 ohm inverse centimeter inverse, right? Second question also done so easy. Now third question. So you see, so it's so easy when we see like approach one by one. If we had approached all at once, it would have been tough. So equivalent conductance of 0.005 normal K2SO4. Okay, great. Equivalent conductance of this. So as we know, the formula for equivalent conductance is 1000 into kappa divided by your C equivalent. So kappa we just find it out, right? 1000 into kappa. Kappa is what we just found it, that it is your 7 into 10 to the power minus 4 for your K2 is a 4, and C equivalent is it's given 0.005, and then we'll get the answer as 120.80 ohm inverse centimeter squared equivalent inverse. Okay, and now the last part. Find molar conductance of 0.005 normal K2SO. So we just found out the equivalent conductance. Now they are telling us to find the molar conductance. And over here we need some knowledge about between normality and molarity, or what we can do is we can use the equation that I just showed you, that lambda m by lambda eq is equals to molar mass by equivalent mass, right? So molar content is lambda m. What is the molar mass? The molar mass for K2SO4, if we find it out the molecular weight, it comes out as 130, and the equivalent weight will be 65, right? Why 65? Because I told you like equivalent weight is your molar mass by charger valence, right? So this will be like so 130 by 2, charger valency over is 2. As you can see, K was 2 plus, SO4 was 2 minus, so this will be 130 by 65 into your lambda equivalent, which is 140.8. So give you to 81.6 ohm inverse, centimeter square, mole inverse. So those are the things, and so practice these things, and now we'll come to some other aspects as well. Okay then. So along with that, you should also know that the molar conductance at infinite dilution, the molar conductance at infinite dilution is very high, in the sense that lambda m is equals to lambda m dot minus k root c. It is given by this lambda m. Should remember this formula, that lambda m is dependent proportional to root of concentration. Sometimes this is asked. Okay. Okay. So the your transport number now. So transport number, as you know, transport number is equals to the current carried by current via by anion or cation divided by the total current. Transport number is given via T plus T minus equals to 1. Okay, so current, like transport number of cation transport plus transport number of anion is equal to 1. So T plus is equals to 1 minus T. So if you just find out T plus or T minus, or it's given, you can just find out T minus as well. Okay. Okay then. Now let us look into some problems. And okay, let me just give you some more advanced concepts. As in your Gibbs free energy, right? So we all know that Gibbs free energy del G is equals to del H plus T del S. This is called thermodynamics and a mixture of thermodynamics and electrochemistry. So we know this equation, we also know this equation, right? And from Maxwell's relation, if you know like Maxwell relation, you also know that del G by del T constant P is equals to minus S, or I think it was over here in a different form. Yeah, so delta G is minus delta S. Okay, so what we can do is, we know all this stuff, and we can write this del S as plus T. Okay, simply using thermodynamics. Okay, and using these two also, we can write what, that delta of del G delta of T constant P is equals to minus del S, and this is also equals to what, minus NF of delta of E delta of T at constant P. So we can write from these two now that NF delta of E delta of T at constant P is del S. So this is a very famous used in calculation. So you see uh, how it's done. We just like correlate some equations and mathematics. I said it's just mathematics and some concepts which you use, right? So, and what else? Okay, so I can also write like this part. Okay, so this was one thing that I wrote, LG del H plus T. So I can also write this as your minus NFE cell is equals to del H plus T, and instead of del S I'm writing this, your TNF del E del T at constant V. So I can cut NF out over here, and this will be by NF, right? And okay, so I can have like, okay, so this I will have E cell over here is equals to minus del H by NF. Okay, and this will be, so did I make any mistake over here? Let me just see. I didn't make any mistake, right? It's fine. So this will be minus T del E by del T at constant P. So I'm just playing with some equations. Okay, and these are actually asked in form of numericals. Okay then, and I'll come now to the famous concept of, this was thermodynamics and electrochemistry next. Famous concept of ionic strength. So ionic strength, that is I, okay, is given by half summation of Mi Zi square, where Mi you can say is a concentration, or you can say, as I said, half Ci Zi square, and Zi is a charge, as you have guessed it. So let us look at it for, if we have 10 molar Na2SO4, what will be its ionic strength? So let us now break this part first. Na2SO4 is actually what? It is 2Na plus SO4 2 minus, right? If N is given 10 molar, if this is 10 molar, we have 2 in front, this will be 20 molar, this will be 10 molar, right? Now let us find the concentration. It's half and summation of Ci square. So for plus first for Ni we will see. Okay, first for Ni what we have is the concentration is 20 molar. So 20 into what is the charge of Na? Sorry, Na. It's not Ni. It's Na. So what is the charge of Na? It's plus 1. So Zi square, Ci Zi square plus your, the Ci for this, that is 10, and the Zi for this is 2, right? It's about 2 minus, it's 2 square, and this will give us our value, which is 30 mole per liter. And now related to this concept only, okay, sorry for this, and okay, moles per liter. Related to this concept only is our mean activity coefficient. Mean activity coefficient, which is given by your log of gamma plus minus equals to minus a z plus z minus root of I. I is the ionic strength. A has a constant value of 0.509. Z plus and Z minus are the charges. Okay, so that is it. And okay, so that is more or less of it. And now we'll look into some numericals. Yes, some more numericals, as you might say, because numericals are most the important things, right? Okay, then I hope you're enjoying the class, and I see a lot of people are watching my classes. Wow, I never imagined that I'll be such a famous teacher. I'm really blessed, and let me now show you some numericals. Question. Okay, this is a very famous question taken from GATE 2007. Question is this: Fe3 plus goes to Fe2 plus goes to Fe. Okay, and it is given that EMF of Fe3 plus to Fe is 0.4 volt. EMF of Fe2 plus to Fe is minus, it's minus 0.44 volts. So you have to find out what? You have to find out Fe3 plus to Fe2 plus, what's the EMF? Question mark. So see, the Fe3 plus to Fe, the EMF for this is given. Fe2 plus to Fe, the EMF for this is given. What we have to find out? This one. This is question mark. The formula for this is your that Ne is equals to N1E1 plus N2E2. So this is our N1E1, this is our N2E2. This whole thing will be our Ne. N is the number of electrons, E is the EMF. So what is the number of electrons we require for Fe3 plus 2Fe? We need 3 electrons. So it will be 3 into, what is the EMF for Fe3 plus 2Fe? It is 0.4. It is 0.4. Just replacing values right now. For N2E2, how many electrons we need for like N2 and E2? We need your one electron, right? One electron only. And what is the EMF for Fe2 plus 2Fe? It is minus 0.44. 0.44. We don't know Fe3 plus to Fe2 plus, but we know only one electron will be needed. So it's 1 into E1. We have only one variable, all are constants. You can just easily find it out via mathematics. Okay, and that will be like in volts, because other things are also in volts. So that is how you do it. Let us now come to a question of solubility product. Okay, so it's given KSP, which is solubility product of M2X3, is given as 2.2 into 10 to the power minus 20. And it is also given that a solubility of M2X is equals to 2 into solubility of M2X3. So it's given, find KSP of M2X question mark. So we have KSP of M2X3, we have solubility relation. So you know, right, solubility product is actually the multiplication of the solubility raised to their power of the coefficients. So we just need that concept only to do this. So M2X3 solubility product is given. So it's actually equal to 2M 3 plus 3x 2 minus, right? Why 2M? Because we have to balance it. Why 3 plus? Because that is how it's formed, right? When the valency of M goes to X, the valency of X goes to M. That is how what we learned in class 8 and 9, right? And so suppose this is 1 in initial. So this is a general procedure that is used in chemical equilibrium also, and in ionic equilibrium also. This is actually a question from ionic equilibrium. And this concept is used very much. So initially the reactant is taken as just like 1 mole or something, and this is taken as 0. And after some time, after t time, suppose some component of it dissociates, and that some component is S. So S is dissociating, and there is 2 in front of it, so like 2S will be formed here. There is 3 in front of it, so 3S will be formed here. So as I said, the solubility product is our product of solubilities raised to the power of their coefficients, right? So the solubility product KSP is equals to 2S whole square into 3S whole cube, right? So this will be equals to 2S. So uh, why it's whole square? Because there's 2 in front. Why is there cube over here? Because 3 in front. So we don't know, we know the solubility, the S value we don't know, but we know the KSP value. The KSP value for this is your 2 into 2 into 10 to the power minus 20. And if you solve this part, it will be equal to 4s squared into 3s cube. This will be equals to, sorry, this will be 27x cube. 4, this will be 108 s to the power 5. And from this you can find out s, which will be equal to something, right? And it is given that the solubility of M2X is 2 into S. So we have found out S. So solubility of M2X will be your, you can say 2S. You can say like it is S prime, solubility of M2X is S prime, and it is actually with the value of 2 into S. So what is the KSP of M2X? It's very easy. M2X again dissociated. This will be your 2M plus x2 minus. You take this as 1, 0, 0. 1 minus S prime, because we have taken it as S prime over here. So 1 minus S prime. You can say this is like 2S prime, and this will be S prime. So your KSP will be, so see, we have found out S prime as well. Suppose we get a value, so this is a very big calculation I'm doing. Suppose I'm saying suppose we are getting something like 10, So it's s to the power 5. So it's like, oh my goodness. Suppose we're getting 10 to the power 2. So this will be our s prime will be 2 into 10 to the power 2. This is just like assumption that value, I don't know what the value is, it's not given also. So I'm just saying. So the value of s prime is 2 into the power 2. So the KSP will be 2s prime whole square into s prime. So, and you just put this value over here, you get the case value of m2x. So that's how we do it. It's pretty easy, right? Okay. Now let us take one more question. So question is this, that Ag plus I minus Agi plus electron, and then Ag is Ag plus electron. So this is E dot equals to 0.152 volts. So E dot is equals to minus 0.8 volts. Okay, they are saying find log KSP for AGI. So find the celebrity product of AGI. So AGI celebrity product, if you find out, so you need to know the how it dissociates. It dissociates into Ag plus I minus. So you need this in the product side, and if you need this in the product side, and you have these two equations, right? So you need to reverse this. This needs to be reversed. So let me just use the green pen right now. This needs to be reversed. Why? Because this is Ag plus and minus in the reactant side, but we need this in the product side. And our okay, there's a mistake. There was no plus over here. Okay, there was no plus. So let us again look into this, because it's only one ion, like one minus and one minus on both sides, so it's matching. So what will actually happen is, so we have Ag plus over here, but I minus is over here. So we need to reverse this as it is, because we need both of this on the product side, Ag plus and I minus. So if we do that and we reverse it, what we get? We get Agi plus electron giving you Ag plus I minus, and over here we have Ag giving you Ag plus electron. So Ag gets cut. Finally, electron and electron gets cut. We have Agi giving you Ag plus I minus. So it's right, right. So we got the right form. All we need to do is reverse the value of this. This will be minus 0.152. This will be same. So this will be plus 0.8, and this will give our E dot value, which will come out as 0. Your so E dot is what? E dot is your the value of E dot is E cathode minus E anode, right? Or E right minus E left. Okay, and so over here, what was the cathode? So which one is getting reduced over here? So this is getting reduced. This is getting oxidized. So the value of E dot will be that, because see, how is it reduced? Because electrons getting added. So this is getting reduced and this is getting oxidized. So this is actually getting reduced. So that the value will be minus 0.152 minus of your 0.8. So the value will be minus 0.952. And they are saying find log KSP. Log KSP normally find in equilibrium conditions, right? We can think of like that, and therefore E cell will be 0. Therefore, if we apply Nernst equation, which is nothing but E is equals to E dot minus 0.0591, because at normal temperature conditions we are considering by RT, like RT by NF log of KSP. Okay, we can take this log of equilibrium constant or KSP. So E dot we know this is 0, this is minus 0.952, N is 1, KSP need to find out. So we can do it, right? We have to just change size and we can find log KSP. That's how it's done. Now let us look into a problem which uses both thermodynamics and as well as your electrochemistry. So it's given over here that E dot volt is equals to minus 0.01 minus 1 to the power minus 4 T minus 298 minus 2 to the power minus 6 T minus 298 whole square. Right. And so see, and it is said that we have to find out E dot is given, we need to find out our entropy and enthalpy. So we just saw that how it is related, right, via these equations. So if we do the same thing, we'll get minus NF, like del of E del T constant P is equals to minus of del S. So we'll get cut. So our del S is equals to NF P, right? So this will be equals to NF. So we need to we have a derivative of this with temperature, and if we do the derivative of this with temperature, what do we get? We will get, the first thing will be 0, this will be only, this part will be left, and over here a 2 term will come out. Okay, so what we will have is this minus 1 to the power minus 4, okay, minus of 2 into the power minus 6 into 2 and T minus 298. So this will be our, and n value we know, which is, okay, the n value for this equation, there's a big equation given, the n value for this is 1. Okay, therefore if we put the t value, and the t value is given as 298 only, so if we put t value over here, so this part will be get 0, and the answer will we get is our minus, so it's not minus, it's 1 into 96500 coulomb into minus 1 to the power minus 4. This will be our answer, minus 9.65 joule per Kelvin. And now they're telling us to find enthalpy. Enthalpy was del H del G plus T del S. Del G, because we know what del G is equals to del H okay, there was I think mistake I did in the before equation. So del G is equals to del H minus T del S. Yeah, this is the equation, thermodynamics. So del H is equals to del G plus T del S, and del G will be minus NFE, and T is equals to del S is, so we know del S is value is this, and the E value, okay, so what we do for the E value is that, so we have the whole E equation over here. Where did we get the equation? Yeah, so this is our whole E equation. Okay, all we need to do is put the T value as 298, so these two terms will get cut, right, and only the first term will be given, that is 0.01. Okay, so we have this, so it will be minus 1 into 96500 0.01 plus 290, that is T value, minus 9.6, which will give us the value of enthalpy. Last question for the day. Okay, so this is a very Good question, I would say, because related to some practical chemistry, right, which you do in lab. So we have a titration of Fe3 plus versus Ce3 plus titration. We need to find out the EMF in two cases. Number one case is when 50% of Fe2 plus is titrated. Second case is when 80% of Fe2 plus is titrated. Okay, so you see the two conditions, like Fe3 plus CS plus versus Ce3 plus titration in two cases when your 50% of Fe2 plus is titrated, and then second case is when 80% of Fe2 plus is titrated. So, and we also, it's the value of EMF is given. EMF or Fe3 plus to Fe2 plus value is 0.77 volt, and your log of 2 is 0.3. It's just given if you don't have calculators, but now these days we have calculators in most exams, so it's fine. So the answer this, the formula that we need to apply is that E is equals to E dot, as we know, minus 0.0591 by N log of 1 by Mn plus. So here is the trick, that log of 1 by M plus, and M plus is the amount of concentration remaining, okay, not used up, it's the remaining part. Similar to the first order kinetics, if you want to relate some things. Okay, so first of all, you need to find the E dot value. What is the E dot value? 0.77. So this is minus 0.0591, and N is 1 over here. Okay, so what is the amount remaining in the first case? It's 50%, so it's 50 by 100. You do this, you get the value, right? And it's log 2, so log 2 value was given over here. The second case, what will happen is that 80% is used up. So how much is left? 20% is left. So 0.0591 by 1 log of 100 by 20. Get 0.739 volts. So that's the answer. Okay, you understood then how easily we can do it. Great. So these were most of the questions from electrochemistry. I'll just try to see if there are. Okay, these were actually most of the questions. So just look over these questions, and I believe you'll be able to answer most things. Practice the things again and again, and you'll be thorough with it, and you can answer most questions. Have a great day. God bless, and see you soon. Sometime, maybe.